We are doing the 2013, and this will be number 4 for both Calculus AB and Calculus BC. It's a graphical analysis, so let's do this. Let's read the highlights here. So this is f prime, important to note. It is twice differentiable. Let's see, f prime has horizontal tangent lines at 1, 3, and 5. So visually, what that is saying, at 1 and at 3, ooh, I should move that up. And at 5, you have one of these. Okay, what else does it say? The areas of the regions between the graph of f prime and the x-axis are labeled in the figure, so that all is given to us in the picture. The function f is defined for all real numbers. And the last piece is that. So here we go with the question. Find all the values of x on the open interval for which the function has a local maximum. So local, also known as a relative maximum, immediately should pop into your head the derivative changes from negative to positive. So let's look at this. Where is the derivative negative? Wherever the derivative is negative, I'm going to highlight in pink. And wherever it's positive, I'm going to highlight in green. Green, we're in the money. Red, we owe. So that's where the derivative, green is where the derivative is positive. Red, pink is where the derivative is negative. So looking at this is pretty obvious. Where does it change from negative to positive? Here. That's at 1, I should label these real quickly. 2, 3, 4, 5, 6, 7, 8. So at 6, we can see it changes from pink to green, which means the derivative changed from negative to positive. Therefore, we have a relative minimum. So for part A, I will say f has a local minimum at x equal 6 because f prime changes from negative to positive. That was easy. I like that question. Part A. Part B. Absolute minimum. I like this question because it's forcing you to understand the difference between absolute and relative. I'm going to go a little more in depth on this to give you guys some understanding. So what does the actual original graph look like? So I claim from 0 all the way up to 4, the function will be increasing in some way. Increasing more here, less here, more here, less here. But from 0 to 4, it's increasing. I know this graph won't be accurate when I'm going to draw. I'll do it in purple. So the graph, does it give us a starting value? It actually does give us a value 8, but ignore, this graph's not going to be accurate in the sense of right values, but it's going to give you an idea of what it looks like. It's going to go up, increasing, up to 4. From 4 to 6, since f prime's negative, we know the function is going to decrease all the way through that region. And then from 6 to 8, since f prime's positive, we know it's going to increase. So that's a rough picture. I don't even claim to be anywhere close to accurate. But I want to highlight some things. We see, and this isn't lined up right, there's a apparent maximum point there and a minimum point there that should occur. And then you have an endpoint and an endpoint. And because I didn't draw this accurately, you don't know if these are at the right heights. I mean, again, this part here could have dropped lower. This part here could be a lot higher. But if you look at this, this has 4 potential points of being a maximum point and a minimum point. All 4 of those red dots are potential points of absolute maximums and absolute minimums. That's why we say a continuous function on a closed interval will have a maximum and minimum, and they will occur at the endpoints or critical points. So when you read part B, what's the absolute minimum? Your thought should be, I need to find all critical points and endpoints and find the actual value of the function at those points so I can tell if this has a maximum or minimum or where those maximum minimums occur. Now, technically, this point right here, let me see what it asks for. Absolute minimum. So if it's asked for absolute minimum, technically, you could ignore this relative max. It can't occur there. So you could justify and say, at 4, there's a relative max because f prime changed from positive to negative. Therefore, it cannot be an absolute minimum. Therefore, I'm going to ignore it. That is perfectly valid. Or you can just check those points also. So what I'm going to do, I'm going to erase all of this because I already did that. And let's just write right up here what we're going to do. So first, you want to find the critical points. What are critical points? It's where the derivative is 0. So I'm going to tell them f prime of x equals 0 at, and I will say x equals 4 and 6. Those are the critical points. Now, how do I find the absolute minimum? Well, I have to find the y value at the endpoints and the critical points. So I'm going to find f of 0, f of 4, and again, you could ignore 4 if you explain that's a relative maximum, but I'm just going to throw it in here because it's pretty easy on this problem. And the endpoint is going to be 8. So if I find the y values at the endpoints and critical points, the biggest one must be maximum, smallest one's minimum. So we are given this information. F of 8 is 4. F of 8. So using the fundamental theorem, this would be f of 8 plus the integral of the derivative, this fundamental theorem, f prime from 8 to 0. Because what this is going to do, if I integrate f prime from 8 to 0, it tells me how much f changes as I move from 8 to 0. So if I know that how large f is at 8, and I add how much it changes as it goes from 8 to 0, that gives me the value of 0. Like I said, this is easy. F of 8 was given as 4. And the integral from 8 to 0, we're integrating backwards here. We're going here to here. The integral from a graph is the net area. So it's going to be 7 plus 6 plus 2. What is that? 15 minus 3, which is 12. So that's going to be the net area. But since we're going backwards, that's going to be negative 12. So there is f of 0. F of 8 was easy. That's already given as 4. F of 4 will be f of 8 plus the change from 8 to 4. The change from 8 to 4, so we're integrating backwards from here to here. So normally it's 7 minus 3, which is 4, but since we're going backwards, that's minus 4, which is 0. And then f of 6 is the starting point that we know, plus the integral from 8 to 6. So it starts at 4. If you integrate from 8 to 6, you're going backwards. So instead of being a positive 7, it's going to be negative 7 minus 7, which is negative 3. So the question is, where is f the smallest? Clearly, negative 8 is the smallest number. So let's read the question. Is it asking for the smallest value or the x-coordinate? Determine the absolute minimum value. So we're done. We just have to write our conclusion. Therefore, -8 is the minimum value of f when x for x between 0 and 8. That is B. 2 more to go. C. On what open interval contained from 0 to 8 is a graph both concave down and increasing? Okay, we can do this. I want to do this on top, so let me erase all this. I probably shouldn't have erased all of that, but it's okay. And all of this, I wish I had a way to erase all this faster, but ooh, sorry, OCDers. Get rid of that. Okay, this one's kind of tedious, so let me write on top what they want. So they want concave down and increasing. So I'm going to give myself a note. Concave down and increasing. That's what we're looking for part C. All right, I get to use cool colors. I wished I didn't erase this. This was all green because f prime's positive. Then this was pink because f prime's negative. So what am I going to tell you about those regions? So the green regions, f prime's positive, so f is increasing wherever the function's green, f prime's green. And f is decreasing whenever it's pink. So we can write that in words for that. But then we also need to know concave up and concave down. So I'm going to do concave down in red. So from here to here, and from here to here, something special is happening. In those red regions, f prime is decreasing. And this I'm writing here, we're going to restate all this above, but if f prime is decreasing, its derivative will be negative. That's both red sections. All right, let's pick another color. I like the dark green. No, we'll do purple. So from here to here, and from here to here, what's special about that section? F prime is increasing. And if any function's increasing, its derivative will be positive. So that's what's true about both purple sections. So the shaded green is increasing. The shaded pink is decreasing. The solid red is concave down. The solid purple is concave up. So we need to write that in words. So that's what we're going to do above. But we just want concave down. So I'm going to just do the concave down, and we want increasing. So I'm just going to do the increasing. I'm not going to do everything else. So I'm going to say f is increasing on what intervals? 1 to 3. And what do we do in 8, 7, 5? 5 to 8. And the reason? Because f prime is positive on those intervals. All right, so we have the f is increasing section. Now we need concave down. that's going to be on the red sections, solid red. So to get concave down, first we need the second derivative negative. So we're going to say f double prime is negative on which intervals? 0 to 1 and 3 to 5. Whoa, dyslexia. Why? Because f prime is decreasing on those intervals. Do you like how I changed from printing to writing? I'm actually like the writing better, so I'll continue with that. Now, we have f double prime negative. Now we can say f is concave down on those intervals. Why? Because f double prime is negative on those intervals. Bam. So now we have to find where both those are true. So I'm going to pick a new highlighter color, orange. Where do we see both increasing and concave down? So increasing and concave down. Well, in this region, we have concave down and we have increasing. So this is a bueno region. And then we have to look at this region. Where here are we increasing? Because we have concave down here. So only in this green region. So we're going to look at here. So that's our conclusion from 0 to 1 and 3 to 4. 0 to 1 and 3 to 4. So our final conclusion, therefore, f is concave down and increasing on 0 to 1 and 3 to 4. Finito. One more part to go. Part D. So we have a function g, a new function right there. And we want a slope of the line tangent. So in your brain, your first thought should be derivative. Derivative is slope of the line tangent. So we want to find the derivative of g of x. Next, what you should see is you have a function and a function. Box cubed. That is classic chain rule. What's the derivative of box cubed? It's 3 box squared times the derivative of box, which is f prime of x. So we want the slope of the tangent line at 3. So we want g prime of 3, which is 3. What's f of 3? Well, they tell us right here. So that's going to be negative 5 over 2 cubed. I don't know why I have 2 of those thingy-mabobbers there. And then f prime at 3. Now, I guess to make this better, I'm just going to do this. So you're not wondering where that came from. Then let me plug in the numbers. So that's negative 5 over 2 squared. And then we have f prime at 3. Are we given f prime at 3? Yes. F prime at, so here's 3. This is the graph of f prime, so it's 4. Answer, done. Don't simplify that. Please, 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 please don't simplify that. Don't do that. That's dumb. Dumb. All right, we're done. That's it. Let's move on to the last one.